Okay, so we are looking at properties of adjoint functors, and we gave a criterion for having a left adjoint for a given functor. Specifically, we said that given a functor g from D to C, specifying a left adjoint for G is equivalent to specifying an initial object of the arrow category, of an appropriate arrow category for each A in C. So we are asking for existence of a bunch of arrow categories, initial objects for bunch of arrow categories at the same time. Now, I want to draw your attention to something similar that we have seen before, and here it is. Yeah, read the top line. Say that a limit of a diagram D exists what is that limit? It is the arrow, it is the terminal object in an appropriate arrow category. Yeah. So eventually we said that, say that a category, look at this black sentence, say that a category C has limits of shape J if for each diagram D the limit of D exists. Which means for each diagram D, the terminal object of an appropriate arrow category exists. Okay, so the shape of the diagram is fixed, but the diagram itself can vary. Yeah, because D is a diagram, which means it's an object of the functor category JC. That's what we were saying here. Now dualize this whole sentence. What do we say? We say that a category has co-limits of shape J if for each diagram appropriate arrow category has an initial object. Okay, so you understand what's happening here? That this theorem that we just proved, yeah, existence of a left adjoint for a given functor is similar to specifying an initial object. What does that tell us? So let me write all this discussion in the form of some remark. So recall that C has limits of shape J if we are given a choice of terminal objects in the arrow category delta arrow D for all D in JC. Equivalently, C has limits of shape J if delta is a functor from where to where? Delta is a functor from C to JC, okay, has a right adjoint. So basically what we are saying is a category has limits of a particular shape if that statement is nothing but this delta functor, the constant diagram functor has a right adjoint, and that right adjoint is the limit. Okay, so limits are right adjoints. And why do right adjoint functors preserve limits? Because right adjoints commute with right adjoints themselves. That's an easy statement. Yeah, I will write it properly. You understand this? I mean, I have just written the dual statement of the theorem above for a particular functor delta, right? Okay, so let me start writing some easy corollary of the theorem that we have talked about. So the theorem is this, that specifying a left adjoint for G is equivalent to specifying an initial object for the arrow category. Now, what can you say about the initial object? Is it unique? If it exists, is it unique? It is unique up to a unique isomorphism, in fact. Yeah, if it exists, then it is unique up to unique isomorphism, and that's what will give us the next corollary. Okay, so I am going to write down the corollary, that if f is a left adjoint of G and f dash is a left adjoint of G, then f is naturally isomorphic to f prime. What is the proof? So what is this initial object that we are talking about? Yeah, that looks like this. If fa comma eta a, we did this in the proof, and f dash a comma eta dash a are initial in the arrow category, then they are isomorphic via a unique isomorphism. Yeah, this fa comma eta a is the map eta a from A to GFA. Yeah, you remember that? It's happening in the arrow category A arrow G. So these are isomorphic via unique isomorphism, and this unique isomorphism, say alpha A, yeah, from fa to f dash a in D. Yeah, so uniqueness implies that alpha A for A in objects of A is indeed the data for a natural transformation. Okay, and since each alpha A is an iso, what can you say about alpha? Alpha from F to F dash is a natural iso. Okay, so earlier we were not sure whether if at all the adjoint exists, left adjoint exists for a given functor, then whether it is unique or not. And this particular corollary of this theorem states that. So adjoints are unique up to unique isomorphism. Yeah, wonderful. Now this uniqueness can also be used quite cleverly. Okay, so let's call this a simple proposition. It's very simple. We'll combine this corollary with another result to obtain something very interesting. So suppose we have three categories C, D, E, and we have got four functors. The first one is, let's say, F, G, and the second one is H and K, like this. So F is a left adjoint of G, H is a left adjoint of K. Then what can you say about HF and GK? HF is a left adjoint of GK.
So the above corollary,
Uh-huh.
can they say anything about the above corollary if we remove the condition that the every shape has its limit?
The corollary doesn't have limits at all. I mean, the blue result is independent. I just wanted to show you that.
I mean, we have assumed that
Huh?
there exists a limit.
No, this is the definition. C has limits of shape J if we are given a choice of terminal objects. That's a definition. I just recall that in a different language. Yeah, we will use it soon, but we aren't there yet. I just wanted to compare this statement with the dual of the state theorem that we proved last time. Yeah, that's why we discussed that. Can anybody tell me the proof of this? This.
We can just take the morphism, assume eta AB is the morphism from CFA.
Eta AB from, no, we don't use eta. Eta AB. Eta is reserved for unit of the adjunction. Epsilon is reserved for co-unit of the adjunction. We don't use that. We can use some other letter, but actually that's also not necessary. I mean, it's simple. Yeah. If HFA, if we are given a morphism from HFA to C, then that corresponds to what? Under natural bijection, you can transfer H from the left hand side to right hand side as K. Yeah, so this naturally corresponds to a morphism from FA to KC, which again naturally corresponds to a morphism from A to GKC. And that's the end of the proof. Yeah, this bijection, we are taking two natural bijections, so their composition is also a natural bijection, and end of the story. And this is just a remark. Okay, now these two results can be together useful in showing this. So suppose we have a commutative diagram . So here there are four categories: C, D, E, and F. And we have got functors. Let's call this F, G, H, K of functors, each of which has a right adjoint. So this is a commutative diagram. Yeah, which means HF is equal to KG, or I mean, even if you take a slightly weaker condition that HF is naturally isomorphic to KG, that's also fine. Yeah, but each one of them has a right adjoint. Then the diagram of right adjoints also commutes up to a natural isomorphism. Believable? Let me just show the direction of all the right adjoints. So we have a diagram of right adjoints as well, and it doesn't necessarily commute up to equality because that's evil, but we can always ask that it commutes up to natural isomorphism. And the reason for that is, first of all, if F and H both have a right adjoint, then what is a right adjoint for their composition? It's the composition of their right adjoints that follows from the previous result. And similarly for KG. Okay, so both of them are right adjoints, but we know that HF is equal to KG. So therefore, it can have at most one right adjoint up to a natural transformation. So therefore, the right adjoint of HF and the right adjoint of KG are naturally isomorphic, and I'm not even going to write a proof. Any doubts here?
So we are using that the arrow categories formed by isomorphic objects are naturally isomorphic.
Are isomorphic. Yes, that's true. Yes. Any isomorphism between objects A and A prime will induce an isomorphism between arrow categories A arrow G and A dash arrow G. Correct. Okay, so now it's the right time to talk about one particular result, and that has to do with limits. What did I promise? That which functors have got left adjoints, or right adjoints. That's a theorem. But first of all, we have to understand the connection, the simplest possible connection between limits and adjoints. So delta has a right adjoint, namely limit of shape J. Okay, so let's combine these two things together and write the result. Suppose G has a left adjoint. The more technical thing is, suppose G admits a left adjoint. I should probably say that G is a functor from D to C. Yes, just to set the notation, although we are using the same notation. Then G preserves any limits that exist in G. Exist in D, yeah. Okay, so suppose F is a left adjoint of G. Yeah, because we know it exists, we just gave it a name. F is a left adjoint, and assume that both F and G, both D and C have limits of shape J. Then this particular diagram commutes. Observe this. From C to JC, do we have something? Delta, the constant functor. From D to JD, we have the constant functor. From C to D, we have F. F is a functor from C to D. And from JC to JD, we have JF. Yeah, composition with F, namely JF. So it takes a diagram in C to a diagram in D. We have used that. Then this diagram commutes. And all functors in this diagram have right adjoints. Correct? F has a right adjoint, namely F has a right adjoint G. Delta has a right adjoint limit of shape J. And JF, composition with F, has a right adjoint composition with G. So therefore, hence by the above theorem, by the above corollary, the diagram of right adjoints also commutes up to a natural isomorphism. Okay, so let us write it down. I will use a different color to denote that. So this is limit of shape J. This is limit of shape J. This is G and this is JG. Which means what? If I first take composition with G and then take limit, then that is same as first take limit and then take G, which means G preserves limits. Very sleek proof. Yeah, that's how we, commutation property with limits is what we call continuity. Yeah. F of limit of an is equal to limit of f of an. That is continuity, a sequential continuity definition in analysis. So that's the same thing that we have written here. Understood this part? Yeah, so that theorem, it looked complicated, but it's not. Yeah, it just looks complicated, but it has so many useful consequences. Because every time you convert anything in terms of a universal property, yeah, we converted existence of a left adjoint to existence of initial objects in certain category. So anytime you convert it into a universal property, then everything is nicely unique, and if it is unique, then most likely it's also unique up to unique isomorphism. So you just have to identify appropriate universal property in this setup. Any questions so far? Okay, then let's go ahead. Yeah.
So we assume both C and D to have limits of shape J.
Yeah, but if you have only the things which you want, then we will only preserve those. So our statement is quite restrictive. Yeah, you can spatialize it.
Do we really need C to have all limits of shape J?
No. See, I will tell you that this proof, this sleek proof works in the case that both of them have limits of shape J. There is an alternate direct proof which you can obviously write down. Yeah, take a limit cone and then show that that particular limit cone maps to a limit cone. And that will always work. Maybe I will give it as a tutorial problem. Yeah, the alternate proof. Okay, so while we are proceeding, here is an idea. I will give it a name. It's called whiskering. Okay, whiskering is a common terminology in type theory, apparently. And why whiskers? If you look at a cat has whiskers. Yeah. So it looks somewhat similar. See this. Suppose we have C, D, and we have two functors, let's say f and g, and we have a natural transformation, let's say eta from f to g, and we have these two whiskers, yeah, namely one functor here and another functor there. So let's call it h and let's call this k. Then if you compare this diagram, then you have new functors, the compositions. For example, fh and gh. fh is from b to d. Yeah, fh and gh. Now we know existence of a natural transformation from f to g. So does there exist a natural transformation from fh to gh? Yes. So this is like a vertical composing with horizontal. Yeah, it will be written as eta sub h. Okay, what is eta sub h? What is the bth component of eta sub h? It is defined to be eta sub hb, correct. So that's why we write eta sub h. Similarly, you also have this other form, c to e. We have kf and we have kg. What will be the natural transformation from kf to kg? It will be k eta. Okay, k eta, just plain k eta. And what is k eta? At an object c. It is simply defined to be k of eta c. Okay. See, this is not just play on parenthesis. It actually means something. Yeah? K eta sub c, which means it is the cth component of that, which is defined to be the image of the morphism eta c under functor k. Understood? So these two things are called whiskering. Yeah? That's how you compose horizontal and vertical morphisms. What are the vertical morphisms here? The natural transformations, and horizontal morphisms are functors. Okay, if you understand this, then we are now ready to give a characterization of adjoint functors.
So,
Yes.
Eta h is a natural transformation. Can we write eta h as a natural in the form of eta and identity natural transformation from space?
Yes, that is precisely what it is. Yeah, you can have, I mean, I'm not trying to make your life more complicated by not including parallel vertical morphisms. For our purpose right now, it's enough to talk about this. Yes, you can take composition of two vertical morphisms as well appropriately. Okay, so let's look at this important theorem. So suppose f from c to d and g from d to c are functors. Okay, just having two functors is not sufficient for giving the data of an adjunction. The data of an adjunction is the natural bijections. Yeah. So specifying an adjunction f left adjoint to g is equivalent to specifying natural transformations First one is obviously eta from the identity functor to GF, and epsilon from FG to identity, satisfying the following triangular identities. Okay, so what are these triangular identities? You have F and F, you have 1F, and here you have FGF. Okay, so can you tell me some natural transformation from F to FGF? F eta. You understand, that's why we defined whiskering. F eta is a natural transformation over here, and FGF to F, anything which reduces number of functors is an epsilon, anything which increases the number of functors is an eta. So what will be this vertical one? Epsilon sub F. And corresponding identity for G. Okay, G to GFG. Correct. And GFG to this is G epsilon. Okay, so both of these commute. So we are given two functors, F and G in opposite directions. If we know existence of two natural transformations which satisfy these two properties, then we know there is an adjunction. And conversely. Okay, so this is important, that we can talk entirely in terms of natural transformations. And here when we talk about natural transformations, we are doing ordinary category theory. So when I say this diagram of natural transformations commutes, it commutes up to equality. Okay. Any questions about the formulation of this theorem?
Where is the delta identity?
A delta means triangular. I said triangular. They both have shape, triangular shapes. Yeah, so triangular identity.
It is not clear what these diagrams are trying to say.
It will be clear. Yeah, I will look at the proof and then it will be clear. Okay, let's try what this is trying to say. So I will purposely do the converse direction first. Yeah, suppose we are given eta and epsilon satisfying the triangular identities. Okay. Now, what do we need to do? We want to define an adjunction. Yeah, what is the data of this adjunction? You are supposed to start with a morphism and you are supposed to associate that morphism from FA to B, a morphism from A to GB. Okay, and that's a very easy process. Let's do this. Okay, so given G from FA to B, define phi G. Okay, phi G I need to define from A to GB. The only way I can go from A to GB is first going from A to GFA via eta, the eighth component of the eta natural transformation, and from GFA now I have little g from FA to B. If I just take GG, then I will go from GFA to GB. So I got phi g. Yeah, similarly, given f from A to GB, define psi of f. Now we have to go from FA. Yeah, so FA to what? Well, FA to FGB we can go by doing FF, and from FGB we can get down to B by doing epsilon. So these compositions are the natural are the associated maps. Okay, both these assignments are natural in both A and B. We are using the natural transformations eta and epsilon as well as functors. So therefore everything will work fine. So what remains to check is that they are inverses of each other. So it only remains to show that they are inverses of each other. Okay, so let's try that. So we have to talk about psi of phi of g. Where will it start? You are already given one morphism and you are supposed to apply f. So take phi g and apply f on each of the components. Yeah, so that is fa, then f eta a to fgfa to fgg to fgb, and then finally apply epsilon b to get down to b. Any problem over here? Did you understand what I did? I took phi g, I applied f on each component, and then when I finally reached at fgb, I just applied I composed with epsilon sub b. Okay, now we just have to play around with this. We have to get down to identity, like this should be G itself. How do we get down to G? Tell me. Can you see some commutative diagram here? Okay, I will draw it for your convenience. See, this is the commutative diagram. Epsilon b and this is FGG. Here what do we get? We have to show this whole map from FA to B is G itself.
The direction of map from FA to FGFA is from down to top.
Sorry?
F eta A is from FA to FGFA.
Yeah.
It's not top to down, it's down to that diagram.
What are you confused about? See, I took this expression, this expression of phi g.
So
I applied f on that.
Is F eta A in that diagram?
Eta a is in that diagram. So when I take f of that,
Yeah.
then I will get f eta a and f followed by f gg, and then finally I applied epsilon b.
So the direction of map
Map should be this.
FA to FGFA, right?
So fa to fgfa, that's what I have written.
Okay, I'm talking about the map, the diagram which you drew in the right.
Oh, but I have another map here. I'm using in this diagram that epsilon is a natural transformation. So I can obviously fill in epsilon sub fa. And over here, I will get g. Can you see this? That this diagram commutes epsilon is a natural transformation. Yeah, if see, this is the part which is common here, fg, and then I am removing that. That is what epsilon does. Okay, so this diagram commutes. So therefore, I can get back to this. So this is equal to fa, f eta a, then fgfa will remain as it is, but fgfa to fa, I can go via epsilon sub fa, and then finally I will just have a g. Okay. If you agree with this, then look at what these first two morphisms are. F eta a followed by epsilon sub fa. Look at the first triangular identity. We know that it is satisfied. So that is an that is a commutative diagram of natural transformation. So we have to take its component at A. Then this simply means this is fa to identity 1 fa followed by g, which is precisely g. Yeah, this is happening via the triangular identity. Okay, so similarly, the other diagram. So similarly, phi of psi of f is equal to f. And this part is done. Still confused?
I'm confused about how phi and psi is defined. They are defined on the morphisms.
Phi and psi are defined on morphisms. If you are given a morphism in of an appropriate kind, so given a morphism from fa to b, where a is any object of C and b is any object of D, then we define phi g to be a morphism from A to GB.
Similarly for the psi.
Yes, similarly for psi. We want a natural bijection between appropriate home sets. So this is the natural bijection that we are talking about. Any other questions? This is simple, yeah, compared to the proofs that we have done earlier. Okay, so now we are ready to prove that triangular identities are indeed satisfied whenever an adjunction is given. So the forward implication. Okay, so suppose F is a left adjoint of G. Then eta A from A to GFA, where A is an object of C, E is the data of a natural transformation. Yeah, eta A we obtained. You remember how we obtained eta A? It is a morphism which corresponds to identity from FA to FA. Yeah, under that bijection. So that we know how to obtain. Okay. So for any I mean, maybe I should write the explanation. For given f from A to A prime, yeah, this particular diagram will commute. What is the morphism here? Tell me at the bottom. Eta A prime, correct. So this diagram commutes. Why?
Because this is a natural transformation.
No, we are trying to show that it is a natural transformation. We have a bunch of maps. Eta A is a map, is a morphism. That we know. But why is it the data of a natural transformation? Because no, so we are supposed to look at both the ways to reach from A to GF A prime. First one is eta A followed by GFF, and the second one is F followed by eta A prime. These are both ways, yeah. I will write. So commutes for both ways from A to GF A prime correspond under natural bijection with FF from FA to FA prime. So that's why they are equal. We know that this is a bijection. So we are given a map. Now if you are confused about this, like that's why I did the other part first. Look at what we said earlier. What was phi g at the top? Phi g is take eta A first and then GG. That's precisely what we are doing here. Yeah, that phi g was the correspondent of G. So similarly, eta A composed with GFF is the correspondent of FF. And similarly, for the other one, yeah, we are taking F first and then eta A prime. Eta A prime corresponds to identity of FA prime, and then this is just A. So therefore, everything works fine. Okay, so this bijection, naturality of bijection is used here. So therefore, it is the data of a natural transformation. See, by the end of this course, all of you are expected to at least speak correct category theoretic language. When we talk about a natural transformation, how do we talk about it? Like, this is the data of a natural transformation. So we have to verify the properties, and the data is just a bunch of morphisms. Okay, so if this is settled, then now let's look at this. FA to FGFA to FA, F eta A and epsilon sub FA. This corresponds to, yeah, I mean this is the triangular identity. We want to prove that it satisfies. We showed that eta is a natural transformation. Similarly, epsilon is a natural transformation. Yeah, I mean maybe I should write that. Yeah, similarly, epsilon is a natural transformation. So now we are given this particular composition. What does it correspond to? Whenever we have an epsilon then look at this psi f. What will it correspond to? Look at psi f. Ff followed by? Yeah, but what is that little f? That's what I'm asking. In this particular composition, little f is eta sub a. So this corresponds to what? A to GFA, eta A, followed by just the identity. Yeah, which is just eta A. And what corresponds to eta A? Identity. Yeah, that's the definition of eta A. And hence, epsilon sub Fa composed with F eta A is equal to 1 sub Fa. Yeah, similarly for the other triangular identity. Any questions here? Did you understand what we did here? Yeah, we just looked at the correspondence. If you understand naturality of the bijection in the definition of an adjunction, then all these things are very clear. We are doing some compositions where one morphism is entirely in one category, and then we are trying to get into something else. Yeah, that's the whole idea everywhere. But this is a completely, this particular theorem that we just finished proving, it's a completely natural transformation way, yeah, or two morphism way of talking about an adjunction. One morphisms are functors. Yeah, so this is a two morphism way of talking about this. Okay, so these triangular identities are sometimes useful if you work with them.
What
Yeah.
happens if we relax the equality condition in the triangle?
We are not going to cover that in this course.
I don't know the answer.
There might be 3 morphisms, 4 morphisms. Yeah. So we are not going to cover that. We'll just talk about ordinary categories. Okay, so let's do one very simple result at this point. G from D to C. Maybe I should set up the problem first. So given C, D, F, G and this adjunction, yeah, there are first 2 statements. So G is faithful if and only if epsilon is pointwise apimorphism. And the second statement is G is fully faithful if and only if epsilon is an isomorphism. Do you remember last time we looked at some examples and there was a specific class of examples where we said that G is fully faithful? What was it called? Reflection. Yeah, such an adjunction is called reflection. So the second statement over here is giving you a criterion for testing whether something is a reflection. Now remember, recall, not remember, from abelian groups to groups, there is an inclusion functor Okay, so you include an abelian group A as IA and then you abelianize IA. What do you get? What is abelianization of A?
Quotienting out by the commutator.
Quotienting out by commutator. It's an abelian group. So what is the commutator subgroup? 0. Yeah, so it is A itself. So therefore, A is isomorphic to the abelianization of IA. So that is indeed an isomorphism. Yeah, pointwise isomorphism is an isomorphism. And that's the same thing that happens with each reflection. Okay, so G is fully faithful if and only if epsilon is an isomorphism. So let's try to prove this statement. So given we are trying to prove both of them in succession. A morphism G from B to B prime in D. The morphisms, okay, GG and G composed with epsilon B correspond to each other under the adjunction. Under the adjunction, by that I mean under the bijection of the given by the adjunction. Okay, where is GG? GG is from GB to GB prime. And this one, G composed with epsilon B, maybe I should write it GB to GB prime. And G composed with epsilon B, FGB to B prime. Yeah, FGB to B and then B prime. They correspond to each other. Do you agree with that? Yeah. So therefore, G mapping to GG, we are talking about G is faithful. So G is faithful means G maps to GG. That map has to be injective. Yeah, so this map is injective if and only if G mapping to G composed with epsilon B is injective. When will that happen? Exactly. Yeah, so if and only if epsilon B is an epimorphism. That is precisely the definition of an epimorphism. G epsilon B is equal to G prime epsilon B if and only if G is equal to G prime. Okay, so this is done. Simple proof. So now let's prove the second one. Okay, let me label it second part. So G is fully faithful if and only if G mapping to GG is what? I mean is a bijection. Okay, so in particular if and only if G mapping to G composed with epsilon B is a bijection, right? So that much is clear. So in particular, what can we say? There is a unique G naught from B to FGB such that G naught composed with epsilon B is equal to identity, correct. Identity on FGB. Yeah, because this is a bijection, so we have to cover identity morphism also. Okay, so now this G naught is particularly important. So therefore, epsilon B G naught epsilon B is what? It is epsilon B. Right, I just composed both sides with epsilon B. And
Composed with epsilon B is also epsilon B, so epsilon
yes,
is equal to
so therefore epsilon B G naught is equal to 1 of B, since epsilon B is epi by 1 above. Okay, so we found one-sided inverse. Yeah, G naught was one-sided inverse of epsilon B, and using that epsilon B itself is an epimorphism, we showed that it is a two-sided inverse. Okay, so therefore epsilon B is an iso, and therefore epsilon is an iso. End of the story.
So an epi which is split mono is always iso.
Yes. Split mono plus epi is an iso, split epi plus mono is an iso. Yes. Any questions? So this gives you a characterization for reflective subcategories, and you will also have dual characterizations for co-reflective subcategories. Yeah, if the unit of the adjunction, have we ever written the words unit and co-unit? No, okay. Let me mention them. Yeah, in red. This is the unit of the adjunction and this is the co-unit. So unit and co-unit are important for an adjunction. That's an essential piece of information. And you can test something. Yeah, this is if you start playing around with categories, then this monos and epis and diagram chasing, that's a fun part of doing this. Sometimes, okay, yes. Not all the time. If you don't know what to do, then it can be pretty frustrating. But yeah, you can, you have a nice criterion for right adjoints to be faithful or fully faithful. Okay, now this whole story began with something specific. I mean, we had used these notations eta and epsilon already, and that was the definition of an equivalence of categories. And that time it wasn't really clear to us why we were writing eta as a natural transformation from 1C to GF and epsilon as a natural transformation from FG to 1D and not 1D to FG, because it was anyway natural isomorphism, so it didn't matter which direction we chose. But this is a relaxation of an equivalence. Yeah, equivalence says that on both sides there are two categories C and D, and those two categories are essentially the same as far as categorical properties are considered. Now that we know what categorical properties are, they are limits and co-limits. Yeah, so if limit of a particular shape J exists in one category, then limit of the same shape will also exist in another category and vice versa. Same thing for co-limits also. However, in adjunctions, what we have done is we have relaxed that. We said that one side will preserve limits, the other side will preserve co-limits. And especially in this reflective subcategory situation, I can emphasize the point that I made in the first lecture, that we are asking for an approximation. We are asking for the best possible solution to a given problem. For example, if there is a group homomorphism from a group G to an abelian group A, then it must factor through a universal object, and namely the abelianization of G. Right? So we are asking for a solution but in a restricted setting, and such a solution exists. That is what adjunctions do. Yeah, they give you best possible solutions to some restricted problems. But now it's the right time to connect it back with the original idea. The problem here is, if you see this particular theorem, the triangular identity theorem, then just having two natural transformations is not really sufficient. Yeah, those two so in equivalence of categories also, we have got two functors going in opposite direction and two natural isomorphisms, but these triangular identities are not necessarily satisfied by those natural isomorphisms. Because the important property is we ask for equality in the commutativity of these triangular identities. So equality is literally equality. Yeah, the morphisms, you cannot go to another morphism, another object, another isomorphic object. Yeah, that's important. So now let's write down a statement to that effect. Okay, so this is our connecting adjunctions with equivalence. Okay, so here is the statement: if C, D, F, G is an equivalence of categories, then the natural isomorphisms eta from 1C GF and epsilon from FG to 1D can be chosen to satisfy triangular identities. I mean, it looks like a very minor tweak on what we have, but it is still important. So in particular, if these two natural transformations, the unit and co-unit, they are natural isomorphisms and they satisfy triangular identity, then we call such an equivalence adjoint equivalence. So let me write this name. So it's an adjoint equivalence of categories, between categories. Okay, so here I'm just going to give you a sketch of the proof. You can complete the proof. It's some diagram chasing and commutative diagrams. So yeah, you should do that. So if eta and epsilon don't necessarily satisfy the triangular identities, then let epsilon prime be defined as follows. So, epsilon prime is from Fg to Fg to Fg and to 1D. Okay. So, it might be a bit confusing what I am doing. The last one is obviously Fg to 1D. What is that? The only thing that we know, it's epsilon. Fg to Fg, it is actually this epsilon sub Fg inverse. This is a natural isomorphism. So, I can talk about its inverse, epsilon Fg inverse, and this is F eta G inverse. Yeah. So, here you just have to note something. Note that epsilon sub Fg is equal to Fg epsilon, since beta composed with Fg, since epsilon composed with Fg epsilon is equal to epsilon composed with epsilon Fg, and epsilon is monic. Confused what I am saying? Okay, let me write this. Where does epsilon go from? Epsilon is a natural transformation from Fg to identity on D. Okay, this is also Fg to identity, and then what is epsilon sub Fg? It is Fg, and this is Fg epsilon, let's say, and this is epsilon sub Fg. This diagram commutes because epsilon is a natural transformation. Okay, so therefore, we get that epsilon Fg is equal to Fg epsilon. Too much notation, but it's not hard. And epsilon is monic, so you can cancel it from both sides and get that these two are equal. And then you compute. Yeah, then I'm just going to write verify that you go from Fa to FGFA to Fa. This is F eta A, and this is beta dash epsilon dash Fa. Yeah, verify that this is actually equal to 1 sub Fa. I mean, I am asking you to verify that the triangular identities are satisfied with a modified epsilon prime. Eta and epsilon need not satisfy it, but the modified epsilon prime will always satisfy it when paired with eta. And this is an exercise for you. If nobody does it, then our scribe will definitely do it. Okay, so this is adjoint equivalence. You can always tweak your given natural transformations, unit and co-unit, slightly so that they satisfy the triangular identities. And now this brings us to one of the most important theorems in category theory, that is the converse to this. Look at this result in blue. Yeah, suppose G admits a left adjoint, then G preserves any limits that exist in D. Now actually, when we say any, we are used to talking about limits of small shape. But when I say any, I literally mean any. If it has large limits, then also this same theorem will work. And therefore, the simplest possible version of adjoint functor theorem, okay, so let me write it. Primeval adjoint functor theorem suppose G from D to C preserves all limits, all, not necessarily small, which exist in D, then G has a left adjoint. Okay, so this will be our most basic primeval form of this theorem. But in practice, you can never verify this. You are asking for large size limits and you don't even want to talk about large shapes. So therefore, there will be two modified versions. They are called general adjoint functor theorem and special adjoint functor theorem. Maybe they were influenced by Einstein, general relativity and special relativity. But there will be some extra conditions to verify and they will be set theoretic in nature. And on top of this, like if it preserves all small limits which exist in D and some set theoretic conditions are satisfied, then it will have a left adjoint. So that will be the content of our next lectures.